So let me just get started here. First off, who am I and why am I on stage in front of you? Well, my name's Peter Sobot. I'm a senior engineer on the personalization team at Spotify in New York City. You can find me on Twitter at psobot or tweet at SpotifyEng about this talk. Feel free to take photos and hashtags and all the things the kids do nowadays. If you haven't heard of Spotify, we are one of the world's largest audio platforms. We've transformed the way that people access and enjoy music around the globe. We proudly use Google Cloud Platform to power the experiences that we give to our 200 million monthly active users. We serve more than 40 million tracks to them across more than 79 active markets. We're also today talking about specifically one Google Cloud technology, which is Google Cloud Bigtable. If you haven't heard of Bigtable before, Bigtable is a high-performance wide column store. You can think of it very, very roughly as a key-value store that's distributed across multiple machines and is very, very high-performance and parallelizable. Technically, it's a sparse, distributed, multidimensional sorted map. Bigtable is a non-relational database, meaning that there's no joins. It's not like a SQL database. And it allows for easy scaling by increasing the number of nodes in the cluster. That's essentially the only dial that you get to turn with Bigtable is the size of your cluster. It's scalable to petabytes, and indeed we've scaled it to petabytes at Spotify. It uses wide columns, and again, it's non-relational. So it's not like your MySQL or your Postgres styles of databases. And like I mentioned, we use a lot of Google Cloud Bigtable at Spotify. Across the company, we have hundreds of Bigtable clusters, thousands of Bigtable nodes, and petabytes of data stored across all of those Cloud Bigtable clusters. So lots and lots of usage of Cloud Bigtable across everything that you see in the Spotify app. Some good examples of that are some of these personalized experiences that my team works on. So personalized via Cloud Bigtable are things like the home page. So if you open up Spotify on your mobile app, the very first thing you see, personalized content for you, well, that view is powered both at the surface level and down underneath by Cloud Bigtable. We also power things like Discover Weekly, our weekly playlist of tracks that we think you are definitely going to like this week, by Cloud Bigtable, both at the surface layer, so serving the direct tracks to your phone, as well as underneath to power the recommendations. And another example is the recommended songs view. So if you scroll to the bottom of any playlist that you make on Spotify and see a list of songs that we'd recommend that you add to that playlist because of similarity, that's also partially powered by Google Cloud Bigtable. So Bigtable really kind of underlies a lot of the features that we have on Spotify. If you're not familiar with Cloud Bigtable itself, it allows for very expressive schema designs. So I mentioned before that it's non-relational. And the schema that it gives to you is something like this. You can have a row key, and all of your data is indexed by this single key. So you don't have multiple indices or different ways to cut the data. You essentially have a key that you can use for lookups, and then a value that is this kind of multi-dimensional object here. You can have multiple column families within that row, multiple columns within each of those column families, and multiple values within each cell as well. And those values are all sorted by timestamp. So you can even do versioning in here and have some sort of like expiration of these values as well. And this is all provided to you by the very expressive Bigtable API. And I don't want to get too much into how Bigtable works under the hood, because I'm a Spotifyer, not a Googler. But Bigtable, one very important thing about how it works and how it stores its data is that the nodes in your Bigtable cluster are compute only, essentially. So while you might be able to increase the number of nodes that serve your cluster, that gives you more capacity. But it doesn't change where the data is stored. The data in your cluster is stored underlying in the Colossus storage layer there, which is a Google technology that is not directly exposed in Google Cloud. This means that if you want more capacity, if you want to add more requests per second to your system, you can add more nodes. And this simply reshards the data across your nodes and changes which data each node is responsible for. So this doesn't actually change where the data is stored. It just changes which nodes are responsible for which data. And this will come up later on in the talk about how we can scale Bigtable very effectively. So I'm going to talk quickly about 3 different common Cloud Bigtable usage patterns that we've seen in our usage of Bigtable at Spotify. We have lots of different products, as I mentioned earlier, and they all use some variants of these patterns that we've seen. The first pattern that we see is using Cloud Bigtable as a real-time data store. So using it to serve some data in real time that might be computed offline or in batch. The second pattern that we've seen is using Cloud Bigtable as a caching layer, which allows us to essentially use it as a large distributed automatic cache. And the third pattern is using it as a platform data store, which takes a little bit more explanation, so I'll wait until I get there to talk about that. So first off, if we use Bigtable as a real-time data store, Bigtable allows us to bridge 2 different worlds of data processing. We can do big batch offline data processing that takes lots of resources, lots of time, and lots of different machines, and then dump the results of that data processing into Cloud Bigtable to serve it in real time. This allows us to get very low latency reads and kind of like write this data all at once and then read it multiple times when different clients request this data. This allows Bigtable to kind of bridge these two worlds and do something we couldn't have done before. Right? You can't do this kind of thing if you're reading off of Google Cloud Storage or many other kinds of databases. But Bigtable really handles this load very, very well. The input data for a lot of our different products, for example, let's say Discover Weekly, might come in batch. We might train a model or do some sort of recommendation product in Cloud Dataflow, which is Google's batch data processing framework. And then the results of that computation end up getting stored in Bigtable by simply writing a huge amount of data from Dataflow workers into a Bigtable cluster directly. And the data sizes depend on the application here, but typically we tend to use gigabytes to terabytes for the Bigtable size here. This works really great for write once, read many use cases. So if you have a lot of data that gets written once or written infrequently, let's say, again, Discover Weekly, if we write that once a week, and we want to read it multiple times when users come back to it and keep listening to the same playlist, Bigtable works really, really great for this. And there are some other great features of Bigtable that allow this to be even more maintenance-free and effortless, but I'll talk about that in a second. Another use case that we have for Cloud Bigtable is to use it as a caching layer. So rather than just using it to serve data in real time, which it still is in this graph here, sometimes we'll need Bigtable to cache data in a kind of distributed way so that systems that are stateless can still use this distributed cache to avoid having negative side effects on other systems. So a good example here is if we use Cloud Dataflow in streaming mode rather than in batch mode. Cloud Dataflow can be used to process streams of data, so as more data comes in, you can operate the same transforms and the same operations on new data. And in this case, sometimes we have Cloud Dataflow streams that need to reach out to other services. They might need to talk to backend services or APIs or things like that. And if we did so without any sort of caching, this could very quickly overwhelm these backend services. We could have a stream of data coming in, and if we imagine every single element in that stream results in a request to a backend service, it's very easy to overload that and make that fall over. Cloud Bigtable works really, really well here because we can make a request to Bigtable as a cache first, and we run the risk of otherwise breaking these backend services. So this distributed cache adds this stateful layer around this stateless Cloud Dataflow service. Again, in this application, the cache sizes range from gigabytes to terabytes, but it really depends on the exact application being used here. All right, so our third use case for Cloud Bigtable here, this is a common one that my team works on. This is Cloud Bigtable as a platform data store. And this takes a little bit more explanation here. So we often train multiple different types of machine learning models, especially for music recommendation purposes. And these models have slightly different properties, or they're different versions of the same kind of thing. When we train these models, we want to produce some sort of intermediate data that we can use for recommendation. An example of this is we might embed some data into a certain space, producing vectors in that space. And when we take all this resulting data, it doesn't make sense on its own. We couldn't serve this data directly to clients or to users and say, here, these are your recommendations. These are not recommendations. These are really intermediate pieces of data that can be used to produce recommendations, but they themselves are not the recommendations. So what we use Bigtable for here is as a platform data store to store all of this intermediate data for all of these different models that we might be testing or might be using for different use cases. Bigtable works really, really great here because we can scale this as big as we need to. We can add more models for experimentation. We can have bigger models, smaller models. All this kind of stuff just gets shoved into Bigtable. And then we wrap this Bigtable in a companion backend service, so this green box right here. That companion backend service can manage things like access control, business logic, and caching so that any consumers that want to use this recommendations data can call the backend service and have one unified API for accessing this Bigtable that stores all the underlying machine learning data. So this has been a very, very successful project of ours to use Bigtable in this manner. And this does drive a lot of our recommendation systems, including some of the stuff that I showed you earlier, like the homepage on Spotify. I mentioned a couple times that we do dump data into into Bigtable from Cloud Dataflow. And that can be as easy as these 10 lines of code here. So we have a framework in-house and also open source called Scio. It's from the Latin to learn, apparently. And Scio allows you to write very small amounts of code in Scala in what looks like almost like a DSL to read data from certain places, map it, filter it, transform it, and essentially build up an Apache Beam-style processing graph in Scala. With these 10 lines of code here, we can read data from a Google Cloud Storage bucket here, map that onto what we want it to look like in Bigtable, and then with one single line at the bottom, save as Bigtable there, we can dump all that data into Bigtable all at once. So Scio is really, really useful for bridging these two worlds and doing complex data processing, and it integrates super nicely with Bigtable. I'll talk a little bit more about Scio later on as well, but definitely take a look at this on GitHub if you're interested. I also mentioned that Bigtable has some very nice properties that make it good as a cache. One of those properties is using its built-in garbage collection policy, or its built-in expiration feature. Now, Bigtable allows you to set a maximum age for your data based on the column family and the table that it lives in. This is directly from Google's developer documentation, but this max age parameter says that maybe after 7 days or 30 days, you want the data that you've written to automatically expire from the cluster. And this means that you don't need to do any sort of management of your cluster. You don't need to have another process read over the data and automatically delete it for you. This happens in the background, opportunistically, and you don't need to waste any CPU on it or any of your mind, really. Like, this just happens automatically. This is super, super useful, and you can think of many use cases where if you have a write once, read many application, this can just make your maintenance headache go away. So we'd definitely recommend this. Another thing about using Bigtable for these use cases is that although it does have a very expressive schema design, it's possible for you to use all of its column families and other features like that to express your data in its language. We found that it can be useful to treat Bigtable as a very, very simple map. So essentially a distributed key value store where you have one key and you have one value. So in this example, we've kind of ignored the column qualifier, the column family as well. We just have them as single characters here. Because honestly, all we really need is one big distributed key value store. And if we have these column qualifiers and column families as single characters, that even makes our processing faster. We have to send those column qualifiers on every single request, so keeping those as small as possible is of interest to us. And we found that if we encode our values as protobuf or JSON, as long as we don't need to do any filtering on those values or ask Bigtable to process them before it fetches them for us, this can be extremely efficient and also lends itself well to doing caching in the application layer and other similar things. So Bigtable, while it does have a lot of features, can be used in this extremely simplistic way to get really, really great performance out of it. All right. So let's talk a little bit about scaling challenges. As I mentioned before, we have petabytes of data stored across hundreds of Bigtable clusters. And so we've run into a number of different challenges trying to scale Bigtable to meet our application load. So the first problem we've run into is how to scale the cluster during ingestion. If, as I mentioned before, we're trying to ingest huge amounts of data via Cloud Dataflow all at once into a Bigtable cluster, sometimes we'll easily overwhelm the cluster with that write volume. This is a graph of, actually, I don't know which cluster this was, but you can see that at different times when we're ingesting data, we'll have huge spikes in CPU utilization. And this is not conducive to having a good user experience, right? You want to make sure that when you ingest data into your system, you're not overloading it such that the read requests essentially get drowned out and have a poor latency. So what we found is a good technique is that we'll scale the Bigtable cluster up just before doing ingestion. So we'll start our Dataflow pipeline. And the first thing it'll do is it will change the number of nodes in the cluster that it wants to write into. So you can do this easily via the Bigtable API. And you'll temporarily scale this up by a factor of maybe 2 or 3 or some factor that we've empirically determined makes sense for this use case. Once we scale it up, we'll then ingest all the data at the maximum speed that Dataflow will allow us to do. And even at that speed, we won't impact the read requests. So we'll have still a good user experience during that entire process. And then once that's done, we'll wait a little while as well for the data to settle down and find its right home. Then once that's done, we can drop the size back down again so we're not over-provisioned and spending extra money on capacity that we don't need at all times. So in a timeline, this is what this looks like. We add nodes to the cluster. We'll wait for the cluster size to increase, wait for some additional time for caches to warm and things like that. We'll ingest data all at the maximum speed we possibly can, and then wait for that data to settle. And once that's done, we'll remove those extra nodes to the cluster to keep our costs low. And this solution tends to work fairly well. However, there is a new feature from Cloud Bigtable's team that might make this no longer necessary. And that is the Bigtable replication feature that they've recently launched. Now it's possible to have multiple clusters replicate to each other, or rather, replicate from one cluster to another cluster. And what we found is that if we have a write cluster and a read cluster and set up replication in between them, this can help us solve this problem in a slightly different way. So in this diagram here, at the very top, we have Cloud Dataflow writing a huge amount of data in. That's that very thick arrow. And the write CBT cluster here is taking all those writes in. It might be a cluster that's larger or maybe provisioned differently so that it can accept all this capacity. And then Bigtable's asynchronous replication will take that data from the write cluster and write it into the read cluster automatically. This writing happens in the background. It's not something you need to kind of manage yourself. You just turn it on, and then it runs when it can. This also means that this usage is eventually consistent. So if you need instant consistency for your data, this is not something that you can really use for that use case. But once the data has all been adjusted into the write cluster, at some time afterwards, that data will have propagated through to the read cluster without affecting the read cluster's read latency or anything like that. And that's great. That means that we can get this high performance, and the backend service never really knows that we did an ingestion, and all we had to do was set up replication between two different clusters. Keep in mind, though, that if you use a solution like this, you'll have to keep two clusters up, and doing all that management does take a little bit of extra cost and a bit of extra time. So really pick one of these two solutions depending on your use case. Another problem we've had when trying to scale Bigtable involves optimizing our key spaces. So this graph on the screen here is a screenshot from Google's Stack Driver tool, which allows you to visualize the activity in your Bigtable cluster per row. So the axes here are a little bit confusing. Time is across the bottom. So from left to right, you have time going forward. The row key in your database is from top to bottom. So you essentially have rows that start with A at the top and rows that start with Z at the bottom, let's say. And then the color of each cell here is the activity for that row at that time. So in this graph here, the brightness on the left-hand side of the graph is an ingestion taking place. And then over time, as the ingestion finishes, the colors kind of become more muted to show that there's less traffic over time. But nonetheless, the traffic is kind of evenly distributed. No one row in this database has more reads or writes than any other rows in this database, for instance. So this is a very important property. If some of these rows received a lot more traffic than other rows, this database would not be easily scalable. And I'll talk about why in a second. Let's say we have a key visualizer that looks like this, very similar to the last one, but now there's a bright line across the middle of the graph. That bright line is telling us that one row key has more reads and writes than the rest of the cluster. And that's a sign that this one key, because it's so hot, it's kind of limiting the scalability of our cluster and causing us to kind of waste money on our cluster if we try to scale it up. And let me show why that is. So we're going to do an exercise together. You don't have to do anything, just sit there. But imagine this is our row key space. This is all of the keys in our Bigtable cluster. We have the entire alphabet, and we want this Bigtable cluster to have two different nodes in it. So a two-node cluster with 26 keys. The first 13 go to node 1, and the second 13 go to node 2. This is not something we can configure. This is how Bigtable segments your key space no matter what. So essentially, the keys are sorted alphabetically, or technically lexicographically. And this means that if you add more nodes, it'll just chop up the key space in the same exact way, and each node will get a proportional amount of the key space. Now, there's a big asterisk there in that certain situations can cause Bigtable to kind of rebalance the cluster a little bit more, but you always have this alphabetical setup happening here. So in this cluster, node 1 and node 2 both have 50% of the traffic to the cluster. So the key space is perfectly even. No key is receiving more traffic than any other key, and it's easy to scale this. If we add more nodes, we reshard, and everything gets really quick. And even better, our 99th percentile read time right now is only 10 milliseconds. So if this is a metric that's important, it's certainly important to us, we want to make sure that in the 99th percentile, our read times are still good. So 10 milliseconds, pretty good for this cluster. That's kind of our target. Now, let's say that something goes wrong. We get a traffic spike to a hotkey that starts with J. And J is currently on node 1 there. So with a huge amount of new traffic coming into this one key, what's going to happen to the cluster? And more importantly, what's going to happen to our read time? If we do the math, it turns out that node 1 now gets 90% of the traffic to the cluster, and node 2 only gets 10%. Keep in mind that node 2 is still serving the same number of requests it was before. It's just that there's so much more traffic going to node J that it's kind of skewing the balance between these two nodes. And if we look at the number at the top here, the 99th percentile read time has now shot up to 60 milliseconds. That's pretty bad. If we started at 10 milliseconds, now we're at 60. That's probably going to trip some alarm and wake someone up at 3 in the morning. So if I'm that engineer who woke up at 3 in the morning and is trying to solve this problem, what do? Well, Bigtable allows me to have one parameter to configure, and that is the number of nodes in the cluster. So let's say I'm kind of groggy, I don't know what's going on. I try to fix the problem by turning up the number of nodes in the cluster. And that gives me this, a cluster that has 4 nodes in it, and each of these 4 nodes now has a quarter of the row space. Node 1 contains A through G, node 2 is G through M, node 3 is N through T, and so on. But the key that starts with J there is still receiving a lot more traffic than all the other keys in the cluster. So if we do the math again here, we see that we now have a very unbalanced cluster. Nodes 1, 3, and 4 are each serving 5% of the traffic, which is great. They have a lot of capacity, and they're going to be very fast. However, in the worst case, or even in the 99th percentile case, node 2 is serving 85% of our traffic. And that 85% is much worse than we expected it to be. We wanted to double the number of nodes and thus cut the latency in half. But in effect, we've really only cut the latency down by 3 milliseconds. What gives? Why is it that we can double the number of nodes and thus our cost and not get a performance gain? Well, we did the math. And pull out your phones. You might want to take a screenshot of this. This is the relationship between the latency of your cluster and the ratio of the traffic to your hottest key to the traffic to the median key. To the best of our knowledge, this is what we go off of, and this is how we understand how to scale Bigtable. So if the traffic to your hottest key is very, very high, and the traffic to your median key is very, very low, and the ratio between them is very significantly more than 1, then this is going to limit scalability by a large factor. If the traffic to the hottest key and the median key are the same, that ratio ends up being just 1, and then the traffic to your cluster is divided by all the nodes in the cluster, and you're golden. You can scale as much as you want to just by increasing that number of nodes. It might be more useful to see this as a graph, though, because certainly this doesn't make any sense to me. Here's this plotted as a graph. So let me explain what this means. Across the very bottom of the graph here, we have the number of nodes in your Bigtable cluster. At the very left-hand side of the graph, that's a Bigtable cluster that has 1 node in it. And at the very right-hand side, that's a Bigtable cluster that has 100 nodes in it. So you can turn that dial from 1 to 100 or beyond very, very easily. The 4 different lines on this graph represent 4 different distributions of data in the cluster. So at the very top, we have a red line. That red line is what happens if you have one key receiving 100% of the entire traffic to the cluster. If you add more nodes to this cluster, that will not fix your latency, it will not add throughput, because essentially that one key is still only being served by 1 node. The additional nodes that you add don't do anything because they don't own any data that's actually being used for anything. So that's the worst case scenario. This is why you don't want to use Bigtable for just one piece of data, essentially. The best case scenario is the opposite here. It's the green line at the very bottom. That's what happens if you have flat traffic distribution. No key is more loaded than any other key in the cluster. And that green line is great. That means that if you have 1 node, your latency might be 100 milliseconds. If you have 2 nodes, your latency might be 50 milliseconds. 4 nodes, 25 milliseconds, and so on. Your latency is essentially the traffic to your cluster divided by the number of nodes. That's why we get this nice line here, because at 100 nodes, in theory, each node is only processing 1% of the traffic. So you get a really, really great scalability curve here. Then we have 2 curves in the middle that kind of show why you care about this if you have different distributions of data. If one key receives 100 times the median traffic, that's the orange line second to the top there. You can add more nodes to the cluster, and it will get better. The scalability will improve, and your P99s will improve, but not by that much. And that's because one node is still significantly bottlenecking the rest of your cluster. The yellow line, second from the bottom there, that's another example. That's what happens if one key receives 10 times the median traffic, which doesn't seem like too much, but adding more nodes will still not increase your performance in the worst case. So this is definitely something that we've used to try and re-architect our systems at Spotify to make sure that everyone gets a good experience every single time. All right, so if having your key space designed in a certain way is super important, how do you design your schemas? What are some good tips and tricks to make sure you don't run into this problem? Well, choosing an evenly distributed key space is probably the #1 thing you need to care about in your schema design for Bigtable. And there are 3 strategies I've run into here. They're in order of worst to best. So strategy #1 is not something you should do. Strategy #3 is something that I would recommend doing. So I'll go through them in order and talk about why you shouldn't do them or should do them. So the first strategy for distributing your keys across the entire key space is to hash all the keys. So you could take the keys that you would regularly put in the database, let's say that maybe they're usernames or something like that, and just hash them. Pick a non-cryptographic hash function. Doesn't need to be secure, just needs to be fast. Because the only purpose of this is to distribute this data across the cluster. This works great, and technically, you can do this and you'll get good performance. However, this is not good for a whole bunch of other reasons. If you hash this data randomly, or you hash it with a hash function, you can't use CBT anymore. You can't use your debugging tools. You can't read the key space on your screen because it doesn't really make sense to you. It's essentially obfuscated, and that's not good for debugging or for developing applications. You also can't do range scans on this data. So if your keys have common prefixes, it's very easy in Bigtable to do range scans and say start at this key and go until you hit this key. Well, if your keys are hashed, they're effectively randomly distributed, which is great for performance, but not good for any sort of data locality or sort of like understanding where data is similar to other data. So a good second approach is to reverse all the keys in your key space. So we tried this for a little while. Assuming you have some sort of numeric ordering, meaning that the digit at the very right of your data, or at the least significant digit, changes more often than the most significant digit. So an example of this is maybe timestamps. If you had timestamps in Bigtable, you could reverse the keys, and then the digit that changes most frequently, every second, would essentially scatter your data across all the different nodes in the cluster. This, again, technically works. You could reverse all the keys before inserting the data, and then reverse all the keys when you read again. This is also more human readable and more debuggable because you can see that data there, kind of read it backwards or put it through a script or something like that. And now it's possible to do that. But this is still not great. There's still a better solution available. And that's solution number 3 here, which is to promote the most random field from your data to the row key. So try to find something in your data that can be used to impart some randomness into your row key and move that from the value that you're storing into the row itself. So if you have some sort of a random identifier, let's say maybe it's an item ID or a UUID or something like that, and if that's consistent in your data and it's random but it's deterministic, try to put that into your row key, thus distributing that data randomly across your cluster, but still giving you some business logic you can do on top of that. This preserves readability, uses very little CPU overhead, aids debugging, and allows you to do range scans if those keys are consistent. So I keep talking about these range scans, and I haven't really defined exactly what they are. So in Bigtable, because all the data is ordered alphabetically or lexicographically, you can scan from one key to another very, very simply. You can tell Bigtable to start a scan at a certain place and end a scan at another place, and even do a prefix scan on that, because that's essentially the same thing. If you have a random distribution of your data across the cluster and your key space, you can still do these row range scans provided that you know what the first section of your data looks like. And if you exploit this even more, you can have tiered keys. So tiered keys are where the first section of your key is kind of a superset of all the later sections of the key. And let me talk a little bit about what that means. So here's a very contrived example. Don't do this. It's just for explanation purposes here. But let's say that you're keying your data in Bigtable by keys that look like this. They start with the country that your data is in, the region, the city, and then the district. And all of these form the same key. So your keys might look something like this, where you'd have the country at the first part here, so Canada, followed by the region or state or province or whatever you have there, then a city, and then a district. This means that you can do range scans on this data very, very effectively. If you wanted to find all of the cities in California, let's say, you could ask Bigtable to range scan from the start of USA:California to the end of USA:California. And that would give you all those rows in one query. This is great. However, this still doesn't randomly distribute the data across your entire database, so you have a bit of performance problems here. And one strategy around that is to remove the first part of the key if you know that it has low cardinality. So in this case, there are only 190-odd countries in the world, and because of that, all of the USA data would be at the very bottom of your cluster, at those nodes there, and all the data for certain countries would be kind of right next to each other. So to get around that, you can take this mapping of, let's say, country to region or some other very, very low cardinality mapping and put that into your application. And then in Bigtable, you could store just the second layer of your key forward. There are many more regions in the world, many more states and provinces than there are countries. And now doing this allows you to randomly distribute this data, or not randomly, but put that across the cluster in a way that helps you scale without kind of hot spotting on certain areas of the cluster. Let's talk about one more example here. This is a key design for doing row range scans over data that involves IDs. So this is a real example from Spotify's data. Obviously, AAA1 and BBB2 are not real users. This is all kind of made up, but this is a real task that we have to solve. And this is, what do we do if we want to know what tracks a user has listened to? So if I'm user AAA1 and I've listened to track 1 at timestamp 123, we can store that in Bigtable with a schema that looks like this. We start with AAA1, then the second part of the key is track 1, and then the timestamp encodes exactly when I listened to that. And then if I want to do a range scan and find out exactly when this user has listened to all these tracks, well, I ask Bigtable to range scan AAA1. Give me all the rows that start with this value. And it gives me back hundreds, maybe thousands, maybe tens of thousands of rows. And each row contains both that user ID and the track they've listened to and the time they listened to that track. Now, because this is a tiered key structure, I can go even further. I can say, tell me not just when user AA1 has listened to this track, but specifically track 2. So if I do a row range scan from AA1, including track 2, I'll get all the different plays that user has had of that track. And that gives me all those rows that are kind of contiguous next to each other in that Bigtable cluster. So this is a super useful technique to try and put your data in a format that will be both scalable and performant across Bigtable, but also in a way that you can still get this kind of performance you would expect out of a relational database with multiple indices. OK, I'm just running along here. This took less time than I expected. But let's talk a little bit about open source. So I mentioned earlier we have some tools that are very, very useful. You can use this in your own pipelines and get your data processing done much quicker with some of these tools. So we love open source. We have a lot of open source projects on GitHub. If you check out GitHub/Spotify, you'll find these projects and many, many more. The first project I want to talk about is a project called Scio. So like I mentioned before, Scio comes from the Latin to learn. It is a Scala-based framework for Apache Beam and Google Cloud Dataflow. And it's inspired by Apache Spark and Scalding. It's fairly popular in the open source community now. It's got a couple thousand stars on GitHub, if that's a measure of popularity. And we use this very, very heavily internally to try and do all of our data processing. So like the example I showed you before, this allows us to, let's say, grab data from GCS and dump that into Bigtable with maybe only 10 lines of code. We could also do complicated data pipelines. You can map, filter, do all the operations you'd expect from a functional programming language, but across large sets of data on Cloud Dataflow in the cloud. So Scio is super, super useful. Check that out on GitHub. There are lots of tutorials and other documentation available, and we'd love to see you start using that. Simple Bigtable is the second thing on the slide here. This is a simpler, more asynchronous Bigtable client for Java and Scala. Now, the official Bigtable client works just fine. It's just a little bit verbose. So what we did was we wrote a simpler client. It's based on the Java builder pattern, and it allows you to do asynchronous operations against Bigtable with a very small amount of code. This also powers a lot of our production experiences. When I mentioned earlier that Discover Weekly and the homepage and stuff like that is all served at a Bigtable, it's going through this library. So this is production-ready code. Try to use that, and you'll see your Bigtable interactions become much terser in your code and easier to work with. And finally, I want to talk a little bit about a project called Annoy. And Annoy is a library for approximate nearest neighbors calculations. What that means is if you're doing machine learning and you have representations of data, Annoy allows you to select similar data in spaces. I'm not doing a machine learning talk here, so I'm not going to get too much into it. But it's approximate nearest neighbors, and the OY, I think, stands for oh yeah. But Annoy, again, on GitHub, very popular, lots of stars, very performant library. Not the most performant library in the world, but it has great support, bindings for most major languages, and it's very widely used in the community. So try to use Annoy if you have machine learning tasks that could use nearest neighbor lookups. And with that, I've breezed through this talk. Again, my name is Peter Sobot, senior engineer on the recommendations team at Spotify in New York. Tweet at me at psobot or at SpotifyEng. And please do give feedback in the app there, in the Google Cloud Next app. This feedback goes back to the Google Cloud team to figure out which sessions to have next time. Thank you so much for your time.